The first part of the problem is to solve the biochemical oxygen demand, or BOD decay. We use this differential equation where L equals the amount of oxygen equivalent of the organic chemicals remaining in milligrams per liter, and KD is the deoxygenation rate constant, and it's set at 0.55 per day. The first way to solve this problem was with the Euler method. Our delta T is 0.5 days, and our times period is from 0 to 6 days. Our initial condition is 15 milligrams per liter. Inside the for loop is the initial condition plus the time step and the derivative of the previous y value. So then we run the program and modify our plot to fit the screen size, and you can see that the rate of decay decreases as time goes on. The next method we use is the Predictor-Corrector Method. The time step is still the same, the time is equal, initial conditions all the same. The y predictor is essentially the same thing as the Euler method. The next part of the for loop is to take the average of the derivative of the predictor and the derivative of the previous y value and multiply that by the time step to get the change of the previous value and the current value. When you run the script, you can see there's a similar trend with the previous result. The next method is the Runge-Kutta Method. All the previous values are the same. In this one, the next value is determined by the present value plus the weighted average of 4 future increments. And once again, you see a similar result. Next, we will use Symbolic Matlab. And in this SYMS line, we have L and T. We don't need T, but it still works with it in there. And you will see a similar result just like before. Okay. So we combined all of the scripts into one, and plot them all in one graph, and you can see that the result of the Euler method is much different than the other three. So when we zoom in on the value at 1.5 days, we see that the Euler method gives us a value of 5.716 milligrams per liter. For the symbolic and Runge-Kutta at 1.5 days is 6.574 milligrams per liter. And the predictor-corrector value is 6.658 milligrams per liter. The next part of the problem is solving for the dissolved oxygen concentration. The variables you need to know are DO subscript S, Kr, or the reaeration coefficient, and the relaxation index. The values are given in the Word document. The first thing that we need to do is describe dl over dt as a function of t. So we will use Symbolic Matlab to solve that equation. The resulting answer gives us our dl dt as a function of t. Since we now know dl dt, you can see that our differential equation is now just a function of t and do. Next, we will solve the do concentration using the Euler method, and our relaxation index values m equaling 0.75 and 1.25. You'll also notice that our dissolved oxygen at saturation is 9.17 milligrams per liter at 20 degrees Celsius.
Incredible job wasn't done here. Nice job.
And then figure out the dissolved oxygen concentrations using the Predictor-Corrector method. So the next thing we're going to do is compare these results to the result of the relaxation point equaling 1 by using Symbolic Matlab. All of the methods together are shown here, and the minimum values are: when the relaxation index equals 1.25, the Euler method gives us a minimum DO value at 1.5 days. The others have a DO concentration at a minimum value at 2 days. You can see the results on your own. Based on the equation and the results from the graph, the higher the relaxation index, the lower the dissolved oxygen levels will be.